So this video is going to be on sets and subsets, and this is basically the introduction to sets. The idea of a set is actually quite easy. A set is a group of objects, or a group of objects of any kind. Sometimes they're numbers, sometimes they're letters, sometimes they're things, right? So we might call a set A, and we're going to say A equals, and what that means is that the equal sign here in this case says this is what's in the set. So like, for example, A equals 1, 2, 3, 4, 5, and that's the set A. On the other hand, we might see B, and B equals, okay, we'll have it A, B, C, D. We're going to see in some other instances that we might have what's called a set of sets, like C, and C will be, and we'll have these curly brackets, and it might be the set A. That's just a set with just the element A in it. The set AB, and the set ABC. And that might be what's inside of C. Okay? So what we're seeing here with all of these sets is that they are groupings of elements. What you also want to notice is that we have no repetition here. So sets do not have repetition within them. Okay? Basically, we are every element is going to end up being unique. So even though A and AB and ABC all have A in them, that's not actually a repetition of an element in the set. The set A is the actual element, and it's not the same as the set AB, and that's not the same as the set ABC, so consequently, they're not the same set, or they're not the same elements within the set. This set doesn't have any repetition in it. So we want to be actually really careful that when we're drawing out our sets, that there is no repetition in there, okay? So with that stated, if there's a set, say for example, we've got the set D and nothing is in it, then we say D is the empty set. That is a set that has nothing in it. You can almost think of it as like an empty container. So this set has nothing in it, and that's the empty set. Okay? So that's another key idea that we're going to be working with. Then we have this idea of cardinality. And so cardinality is the number of elements within the set. And how we denote it is we denote it as, it looks like an absolute value sign. So like the cardinality of A, this top set A is 1, 2, 3, 4, 5. So the cardinality of A is equal to 5. Okay? Let me rewrite that, make it clear. It's the number of elements in the set. The cardinality of B, because we have A, B, C, D, is equal to 4. And the cardinality of C is actually equal to 3, because it's a set of sets, and there are 3 sets within our set. So C is equal to 3. And then the cardinality of D is equal to 0, because there's nothing within that set. Okay? Only one set has a cardinality of 0. And that is the empty set. So that's the only one that actually has a cardinality of 0. So we've got some key ideas. We've got a set. Sets up it's a group of elements without any repetition in it. There's something called the empty set. That is a set with nothing in it. And then we have this key idea of cardinality, and that is when we count up the number of elements within the set. So now let's look at some big important sets that we have, and these are sets of numbers that we use a lot inside of discrete math. So the first set that we're going to look at here is the set N, and kind of it oftentimes is denoted that way, and that's the set of natural numbers. And the set of natural numbers, we might also call those the counting numbers. That's the ones that kids learn when they're first learning to count numbers. And so that set is essentially, if we think about it this way, it's going to be 1, 2, 3, 4, so on and so on and so forth. Notice there are no fractions within that set. So that's the natural numbers. The second set that we want to look at are these things, and these are called the integers. Okay? And we've talked about the integers quite a lot now. Okay? But the integers are going to be all of the natural numbers, their negatives, and 0. Okay, so we'll imagine that we've got dot, 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 because they go on for an infinity. Say -3, -2, -1, 0, 1, 2, 3, and so on and so on and so forth. The next group of numbers that we have are the rational numbers, represented by Q. And these are all the numbers that we can actually write as a ratio of integers. And so I'm going to use some set builder notation, and this thing called set builder notation. And what we're going to do with set builder notation is I'm going to say this is the set of all x belonging to Q, okay, such that we have x equals a over b, and we'll define that x belongs to, A and B belong to the integers, and B does not equal 0. Okay? And in fact, in this case, we can probably get rid of the x belongs to Q. That's kind of redundant. We can just write it this way. Okay? And then I'll close my parentheses. And what this means, what we're going to see here is a couple of things. One, this symbol right here means belongs to. All right? Is an element of. So is in the set. And we're going to see that in just a little bit. We're going to see that showing up for sets. So it's in the set, right? And then this thing right here, just in case you forgot, it means not equal to. So this set of rational numbers is the set of all fractions, right? We write them as a over b. So in this case, we could see things like x equals 1/2. That happens to be in the rationals. Also, x equals 2, because that equals 2 over 1. That also is inside of the rationals. Okay, so all of the integers end up being in the rationals. So like, for example, x equals -4, that's equal to -4 over 1. Or it's also equal to -8 over 2, so it's also a rational. 0 is a rational number because we could set a equal to 0 as well. All right, so what we get here with the rationals, if we kind of create as a subset, the rationals are all of the integers and everything that can be written as a fraction. So those are our rational numbers. Then we have the last one we're going to have here are the real numbers. And so those are the reals. And the real numbers are well, basically they make up the rationals and all these other things called the irrationals, all right? And they are represented by the real number line. In mathematics, we call the real number line dense. That is that there are no breaks in it. So it's represented by the real number line. These are the things that you use when you're doing like algebra, for example. Okay? And the difference here is that the real numbers are not discrete. They're actually what we call continuous. That is, that density is that there's no breaks in the real number line. The natural numbers, the integers, and the rational numbers, they are all what we would say are discrete. That is that there are breaks in between them. And in fact, there's a very famous mathematical theorem, mathematical proof that shows that you can in fact find an irrational number in between any two rational numbers, right? And so what we get is that there are always breaks in between any sets of rational numbers, even though it kind of looks like they might be really close together too. So n, z, and q, those are our discrete numbers. And it's going to turn out that those are going to be the ones that we're going to use a lot, all right? We're going to be utilizing those a lot inside of our discrete mathematics course. Now the next piece that we have here is something called set builder notation. And set builder notation is a way of representing sets that are perhaps infinite. So we're going to use set builder notation when we actually have a really large set where we don't want to actually order out all the sets. And so what you'll see is, I'll give you an example of this, and we're going to then break it up into its component parts. Let's say, for example, we want x belongs to z, okay, such that x equals 2k for k belonging to the integers. X belongs to, for k belonging to the integers. That's it. Great. So what we're saying right here is we're actually saying we want to have all the values. This is x is an element of the integers, so it comes from the integers, right? This is the larger set that the set here, and we'll call this set A, comes from. Then this is the rule that defines the set. And so in this case, it's all the elements where we can take an integer and we'll multiply by 2. And what you see here is that A is the even numbers. And that's what we're looking at when we look at A. A is going to end up being the even numbers, right? Because it's 2 times an integer, and that gives me even numbers. And so that's set builder notation. So let's take a look at like an example here. Let's say, for example, I have x belongs to R such that the absolute value of x equals x squared. Now in this case, we don't actually have an infinite set. What we want to do is we want to see what are all the elements that actually follow this rule. Well, if I think about this, this is going to be the set 0, 1, and -1. Because those are all the elements where the absolute value of that number ends up giving me x squared. We might also want to say something like this. X belongs to now all the rationals such that, okay, x equals a over 2, okay, for a belonging to the integers. Now, this is all the numbers that we, in fact, can, we could take all of the integers and divide them through by 2. So that basically gives me every single number within the integers. And in addition to that, it will also give me all of the 1/2, 3/2, 5/2, -5/2. And if you think about it, this is actually kind of a neat set. What makes it a neat set is that, in fact, we utilize the integers in order to create it. Right? So we expect that we should have exactly the same number of elements as the integers, and we in fact do. Right? It's infinite, and it is what we call countably infinite, even though it also appears like it should have more than the integers. If you kind of think about it, shouldn't have double the number, but it can't, because the integers are infinite, and we use the integers in order to build this set, so the two sets actually end up having the same exact cardinality. Kind of a trip like that. It's a fun one to think about. There's a lot of ones that kind of work that way, and there are a lot of really interesting proofs in math that kind of use arguments like this. All right, so now let's talk about the last idea inside of this lecture, and that's on sets and proper subsets. So we want to first start out with talking about equality. So we'll have two sets. We have A and B, and they are sets. We're going to say that A equals B if and only if x belongs to A, if and only if x belongs to B. All right, so we're going to utilize that biconditional idea. That is that if x belongs to A, then x belongs to B, and if x belongs to B, then x belongs to A. Okay, so basically what this is saying is that A is going to equal B if every element in A is in B, and every element in B is in A. So those two are going to end up being our idea of equality, right? It kind of makes sense, right? If we look here, example, I've got 1, 2, 3, 4. This equals 2, 3, 4, 1. Even though the two of them are in different order, they actually have the same exact elements in the set. That's not an ordered, neither one of them are ordered sets. So consequently, these two, in fact, are equal. And that's equality. Okay? So that's an important idea. Now, the next thing that we have here is we have A is what we call a proper subset of B. So it's called a proper subset. And A is a proper subset of B if and only if for all x belonging to A, okay, x belongs to B. Right? Or maybe actually let's do it a little bit differently. Let's say x belongs to A implies x belongs to B. Notice in this case, we don't have the if and only if. We don't have the biconditional. Basically, every element in A is also in B. But we have an added thing to, also in B. We have an added piece here to it. We need that there has to be at least one element in B that's not also in A. So, what we want to say in addition to this is, and, so we'll use an and, x, there exists an x belonging to B such that, okay, x does not belong to A. So there is an x belonging to B, okay, such that there exists an x such that x belongs to B, implies that x does not belong to A, okay? And what that basically means is that we've got an x. So let's say that A is a proper subset of B, okay? So that's what this symbol means right there. That's a proper subset. And what we're going to say is that A is a proper subset of B if and only if 1, x belongs to A, implies x belongs to B, and there exists an x such that x belongs to B implies x does not belong to A. So we have at least one x in B that's not also in A. That's the idea. So all of the elements in A are also in B, but not every element in A is also in B. Every element in B is also in A. So the idea here is, say for example, I have 1, 2, 3, 4, 5, and we let that be B, and A will equal 2, 3, 4. We notice that the elements 2, 3, 4 are in B, okay? But then B also has 1 and 5, and so what we can say here is A is a proper subset of B. That is that basically it's like A is contained within B. The last idea we have here is called just the subset idea. A is a proper subset of A is a subset of B. So now this is just subset. And what this is that the subset one is not as strong as the proper subset. Essentially what it says is that x belongs to A implies x belongs to B. And that's it. So if and only if A is a subset of B. And that just essentially says A, the elements of A are all in B. So like for example, we might see something where we're like, okay, we might have the set 1, 2, 3, 4, and that'll be A. And then we have B is going to equal 1, 2, 3, 4, 5, 11. So A is a subset of B. That works. Every element in A is also in B. That's great. Or we might have, say for example, we have B here in this case. We'll call this B2. And B2 is now 1, 2, 3, 4. So it is in fact equal to A. Well, it is still the case that A is a subset of B2. And it turns out that B2 is also a subset of A. And if we have actually this relationship right here, then we have equality. If A is a subset of B and B is a subset of A, then A has to equal B. Right? That's essentially what's happening. But this idea of a subset, we want to be clear that for A to be a subset of B, either A is a proper subset or it is equal to B. That's it. Okay? But it could be either one. So like this idea of subset is a very general idea. It includes both sets that are equal and it also includes sets that are proper subsets. So this kind of opens up and shows us the basics of sets and set notation. Okay? Big things that we have here, we have these things, the ideas of subsets. And you want to make sure that you understand the difference between this notation, subset notation, and this belonging term. And what that means in terms of the difference between sets and subsets, whether or not a group of elements is in a subset or it actually is a set. Because that actually is a key distinction. We want to be really careful about that. Okay? In addition to that, we talked about cardinality. Remember, the cardinality is a very important vocabulary word. It means the number of elements that are in the set. Okay? And we want to start to get better and better at reading set notation because I'm going to start using set notation a lot more. So this completes our first lesson on sets.